Hello, everyone. We're group number 2. Our project aims to build a prediction model for the bridge conditions. In the United States, 42% of bridges were built more than 50 years ago, while 7.5 fall under the structure deficient category, in which around 178 million trips per day are made on them. To repair deficient bridges, it needs approximately $22.7 billion per year. So we have to allocate our budget to the worst first. Deterioration of bridges is one of the main reasons for bridge failures. The existing research on the bridges is always location-specific and/or bridge type-specific without incorporating the weather dimensions. Our study, however, incorporates the bridge data across the United States, considering local weather records and the bridge material, which fills the gap in the domain. The following methodology has been applied to meet these objectives.
Given that our objectives are extracted from the CRISP-DM, so it can be mapped based on a standard data mining process. At the data preparation, we first have explored the attributes that are going to be used on the modeling procedure. As a brief explanation, we gather the proper information and change it to the CSV format. The Python is used for the data flattening and the further analysis in this study. First of all, based on the literature review, the attributes have been reduced. Furthermore, we cleaned the data warehouse from the missing and inconsistent data. For instance, the freeze and thaw missing data were replaced by the mean for each state. And for the number of bridge lanes, inconsistent data have been excluded based on the literature review and web search. The final stage for defining the most influential attributes is EDA, which will be explained later. In this study, 8 assets were selected based on the weather data and the freeze and thaw cycles, so we can have a good range of weather conditions. To flatten the data, we use geographic features. Coordinates in the two data sets have been rounded for the concatenation. With this approach, each bridge can be assigned to a weather data with a half a degree accuracy. Moreover, we used weather data for the neighbors states, so to ensure a matching regardless of the weather station location.
In our project, 3 machine learning algorithms have been chosen, namely decision tree, KNN, and naive Bayes. This would allow for comparative analysis, evaluating each model's advantages and shortcomings, since there is no definitive benchmark. To determine the optimal model from the candidates, the receiver operator characteristics curves will be built. Then the areas under the ROC curves can be calculated and compared for each model. These are the sources of our bridge and weather data in 2021 for this study.
So far, our data set contains 3 target variables measuring the conditions of deck substructure and superstructure of bridges, as well as 31 predictors that consists of 9 categoric variables and 22 numeric ones. Although the categoric variables have been excluded in the literature, we have applied some EDA to figure out their importance. To this end, we used histograms and association analysis. On the other hand, the numeric attributes have been explored using a parallel coordinates plot because of the high dimensionality of the dataset. Also, we have generated the Spearman's rank correlation matrix due to the monotonic behavior of some predictors against the target variables. We plotted the histogram based on material types of bridges and found that different behavior exists. The majority of the pre-stressed concrete got condition of 7, but if we looked at steel bridges, they were roughly distributed from condition 5 to condition 7. The same thing applied to substructure and superstructure conditions. These different behaviors encouraged us to consider material type attribute for the upcoming steps and modeling. From this conclusion, we have performed association analysis based on bridges material, and we also found association between structure type of bridges and their conditions.
Out of our 31 predictors, 22 are numeric. Evaluating the correlation between them and our target labels goes through, firstly, normalizing the data, secondly, through plotting parallel coordinate plots, and finally, through the use of a Spearman rank correlation matrix. The results of which will now be presented according to bridge type. Spearman correlation coefficients extracted reveal 2 things. First, a group of highly influential parameters correlate relatively highly with bridge condition, regardless of bridge type. However, the extent of influence of these parameters on bridge condition seems to be related to bridge material. Further investigations will need to be made. The remaining steps of the work are broken down to 2 phases. The first is the model development and training. The second is model evaluation, used learned metrics, and a comparative analysis for a conclusion on the optimal model for our study. That's it for our presentation. Thank you for your attention.